Good morning, class. Okay, today we will look at the analytical method. Okay, analytical method to solve a PDE. Okay, so this is the name of the method of separation of variables. Okay, so I think that day last week I have shown you what is PDE. Okay, and their solution is the UXT. The solution is UXT if the dependent variable is U. Okay, so now this is the solution UXT. And by method of separation of variable, we aim to find a solution in the form of a product of two functions. Okay, these are the product. Okay, this is the product of two functions. X times t. Okay, x times t. So we aim to have the solution as in this product function. But this cannot be zero. We do not want our solution to be zero. Okay. So from the assumed solution above, okay, we assume our solution is the product function of x times t. So with this assumption, okay, so your del u del x, okay, del u del x means that when we differentiate this u with respect to x, we have a prime. Okay, we have a prime on the x. So that means x prime t. Sorry. Okay, I repeat. When we prime for this del u del x means differentiate u with respect to x. Okay, with respect to x. Our u is x times t. So del u del x means that we differentiate x. Okay, we differentiate with respect to x. We differentiate u with respect to x. So there's one prime on the x. So x prime t. For the del u del t, there's one prime on the t because we are differentiating u with respect to t. For del square u del x square, we have x double prime t. Okay, double prime because we are differentiating u with respect to x two times. Okay, twice. And del square u del t square will be double prime on the t. Okay. So from the assumed solution above, all the derivative can be written in this way. Okay, with these derivative representations, a separable linear partial differential equation with two variables. That means that your PDE can be reduced into two ordinary differential equations. Okay, let's see how we reduce the PDE into two ODE. Okay, we look at this example. We want to present you. Okay, determine whether this is separable. Okay, we want to determine whether this is separable. So we assume, okay, our solution is u, okay, where u is x times t. So this differential, this partial differential equation can be written in this way, because this is ut. Okay, one prime on the t. Okay, x t prime, and ux is x prime t. Okay, when we have a 2 here, okay, that means we have 2 x prime t. Okay, so you have to know how to change the ut, utt, ux, uxx into these representations. When it is first order, there's one prime. Okay, with respect to x, that means the prime is on the x. Okay, ut, that means the prime is on the t, one prime. If you have utt, that means double prime on the t. Then by separating the variables, we can get this. Okay, separating the variables. This is similar to the chapter 1 separable equations, where we can separate the x and t. Okay, totally. Okay, totally separate them. One is x on the left, another one is t on the right. Okay, we separate this completely into one variable on the left, another one on the right. So this is separable. Okay, the PDE is separable. If you manage to separate the x and t, one on the left, another one on the right, this means the PDE is separable. Okay, another example, this one, UT. Okay, UT, that's been XT prime. UXX is X double prime T. Okay, and your U is XT. Okay, your U is X times T here, XT. So when we rearrange, we try to separate the X and T. So here we have X, this one also we have X, we can rearrange. Okay, we put this together with this on one side. Okay, this one stay on another side. So we try to factorize the X. Okay, we try to factorize the X. So we have T prime plus 2T. Okay, and here we have X double prime T. So now we can separate this by move this X to the right, move this T to the left. Okay, then we get the all X on the left, all T on the right. Okay, no matter which one is X on the left or right, it doesn't matter as long as okay, one variable on the left, another one variable on the right. Then this is separable. Okay, any questions? If no, we try this. Okay, determine whether these PDEs are separable.
Yes.
Okay, we change. Okay, you need to change and rearrange the equation. Then only you can see whether it is separable. Okay, T square, your UTT, what is your UTT? Okay, your U is XT. Okay, your U is XT. We assume U to be XT. So UTT will be double prime on T. So we have XT double prime. Okay, X square UXX. UXX does mean double prime on the X. So X double prime T. Then we try to separate. Okay, T. Move the T here and move the X to the right. Okay, then it is separable. Separable PDE. Okay, normally we will let the one with prime on the top. ux. Okay, we assume the u to be x times t. So ux means x prime t. Okay, ut that means xt prime. So is it separable?
No.
Okay, not separable. Okay. X. So what is your ux x? X double prime t. UTT X T double prime. Double prime on the T. Okay, this one double prime on the X. Your U is XT. Okay, equals to 2. Your UX is X prime T. Okay, now try to try to rearrange. We have a T here and we have a T here. Okay. We move this to the left. Move this to the right. And we try to factorize. Okay, factorize the T. Factorize the T. Okay. Then, okay, this T goes to the right. This X to the left. Okay, you managed to separate the X and T, so separable. This one is double prime. Double prime. This one is double prime. So T UX is
D x prime t.
X prime t plus x ut is
X t plus
x t prime plus
u.
u is
X t.
x t. Okay, u is x t. Okay, these two, we have t, but after you factorize the t, you have tx prime x. Okay, it doesn't work. And these two, after you factorize the x, you have xt prime plus t, and it doesn't work. Doesn't work as well. Okay, because we want to separate the x and t completely. So this is not separable. Okay, you see after you factorize the t, here you have x, here you have t x prime. Okay. This one and this one, if you factorize x, here you still have x t prime and t. So not separable.
Kalau kau tiba-tiba kita itu yang deduksi terkait
Okay, x
X prime t.
uxt
X prime t plus
x prime t prime. Okay, this is x ut
X t prime.
x t prime. Okay, try to check. We have this. After factorize x prime, you have the t. Okay, so we can factorize the x prime. Okay, then move this to the left, this one to the right. Okay, next we look at the method of separation of variables in a general form. Okay, in a general form. Now, given a heat equation, okay, given this heat equation along a uniform metal rod, so we want to solve this PDE using separation of variables. Okay, here you are given only the PDE without any boundary conditions and also the initial conditions. So what we can obtain is just in a general form. Okay, now we let our U, the solution, to be x times t. So because of this assumption, your heat equation, this one, your heat equation, UT, this is UT. UT is xt prime. Okay, UXX is x double prime t. Okay, so your heat equation will be this. Okay, now we're separating the variables. So we have this x to the right, this kt to the left. Okay, we let the constant k follow the one in first order. Okay, you can let the k follow the second order, it doesn't matter. Okay, it doesn't matter, but this one, if you let the k follow the first order, it will be simpler. Okay, now with this, okay, with this one, for this to be valid, okay, this equation will be equals to a constant, and this is known as separation constant. P is a constant. Okay, so because of this, okay, if you see this one, x double prime over x equals to P. Okay, when x double prime over x equals to P, x moves to the right, you have Px. When you move the Px to the left, you have x double prime minus Px equals to 0. Okay, another one, if you just look at this part, kt move to the right, you have pkt. Okay, you have pkt. Then you move the pkt to the left, you have t prime minus pkt equals to 0. Okay, that means from this, you can get these two ODE. These two are no longer PDE. These two are ODE. Okay, ordinary differential equation. Okay, one is second order, another one is first order. Okay, so now we want to solve these two separately. Okay, recall this is what we obtained just now. One second order, another one in first order. Okay, now we have to consider three possible cases for the p value. Okay, case one is p equals to 0. Okay, case two is p greater than 0, and the last case is p less than 0. Okay, we consider three possible cases for the p. If we start with the case one, p equals to 0. So if this p is 0, that means we have only x double prime equals to 0, correct? Okay, so this one, we want to solve this. When you have x double prime equals to 0, what is your x? We just integrate, right? We integrate x double prime, you get x prime. Integrate 0, you get a constant. Then x prime, you integrate once again, you get x. So the constant, you integrate with respect to x, you get ax plus b. Okay, this one. Yeah, right on the board. Okay, just now we have x double prime equals to 0. Actually we have x double prime minus px equals to 0, and another one is p prime minus pkt equals to 0. Okay, we have these two equations. Okay, we have these two equations. Okay, for case one, p equals to 0. So that's why when p is 0, we have x double prime equals to 0. And another one, when p is 0, we have p prime equals to 0. We have these two. So this one, when we integrate, you get x prime. You integrate x double prime, you get x prime. Integrate 0, you get, let's say, constant b. Okay, so you integrate once again, you get x. So this one, integrate with respect to x. Oh, sorry, this one should be a first. A. Then ax plus b. Okay, that's why your x, you can also write in this form, x in x equals to ax plus b. We integrate twice to get the solution. This is the solution for this ODE. Okay, and another one, it goes to this one. So when we want to get the t, that means we integrate this with respect to t. Okay, so we get a constant, but we have already used the AB, so here we use C. To get a constant. So your solution, okay, remember this is your solution. UXT is your solution. And your UXT is actually X times T. Okay, meaning that this one multiply to this. Okay, A is constant, A, B, C are constant. So constant times constant, you get a new constant. Let's say A. And then plus BC, another new constant, let's say B. So this is the solution for the case of P equals to 0. Okay, so if you refer back to the slide, okay, you get the same thing. Okay, this one. Okay, and just explain on the whiteboard easier. Okay, now we look at the second case, case 2. P is greater than 0. You don't have to copy because this is given in the slide. Just further explain how you get the final solution. Okay, so if P is greater than 0, we let P be lambda squared, but your lambda is positive. Okay. Lambda is positive. We let P be lambda squared. So if your P is lambda squared, okay, you refer back to this one. When P is lambda squared, so what you get will be x double prime minus lambda squared x equals to 0. Another one is t prime minus lambda squared kt equals to 0. Okay, so this is second order ODE. Second order ODE. So to solve this, what do you use to solve this? Second chapter. Second order or more. We use characteristic equation, right? Second order or more. So the characteristic equation is m squared minus lambda squared equals to 0. Okay. M squared minus lambda squared, because you have no x prime. The one x prime, it will give you the m. Okay, so when you have this, okay, m squared equals to lambda squared. That means your m is plus minus lambda. This is real and distinct. Real and distinct. So your x, what is the solution for the real and distinct roots? You have the C1 E. Let's say positive first. Lambda x plus C2 E negative lambda x. This is real and distinct. This is not complex conjugate because there is no I. Okay, there is no I. Okay, to avoid confusion, I follow the slide. Here the slide use A and B, so I use A and B. Okay, I follow the slides. Okay. So a constant, exponential lambda x plus another constant, exponential negative lambda x. So this is the solution for the x. And now this is the first order. Okay, first order differential equation. So do you still remember how to solve the first order differential equation? Okay. P prime. T prime is dt over dt, right? Because this t, we know that t prime is dt over dt. Minus lambda square k. Okay, this one we just move this to the right. Okay, move it to the right. Positive lambda square k t. Okay, this one move to the right. Okay, this is a separable first order differential equation. Separable. Okay, that's mean uppercase and lowercase of t. We can separate the uppercase and lowercase of t. So this t bring to the left, it will be 1 over t dt. And this one, d lowercase of t, move to the right. You have this. Okay, so on the left you have uppercase of t. On the right you have lowercase of t. This lambda and k are constant. Okay, constants. So this one, when we solve this, integrate 1 over t with respect to t. You get a log t. This is a constant. T plus c. Okay. Then we want want t. Because we want to get the x and t, then we combine x and t to get the u. Okay, so your t will be exponential. When you move to the right, it will be exponential. Log,
Done.
when you move to the right, you get exponential plus c, right? Then this is EA plus B. EA plus B. That means EA times EB. EA times EB. EA times EB. And since B is a constant, EC is also a constant. So we let this to be a new constant, which is uppercase of C. This is lowercase. E lambda square kt. So this is your t now. Because EC, we let this to be another constant. We let this to be a new constant. Okay, so once you get your x and t combine, you get your u, because your solution is u. Okay, always remember your solution is u x t, which is x times t. Okay, so your x is the 1, a e lambda x plus b e negative lambda x times this one, c e lambda squared kt. Then again, when you expand, okay, you get a new constant. Okay, get a new constant. Now we use b and e. Okay. AC, we let AC to be b, a new constant. Okay, so this one multiplied to this one, we can combine into one. So this one plus this, okay, plus lambda square kt. And then this one, BC, we let BC to be E. Combine these two E, we have negative lambda x plus this one. Okay, so this is the solution for the case 2, p greater than 0. Okay, any questions so far? If you understand this one, later it will be clear. Okay, you will be clear with the additional given initial value and boundary conditions. Okay, this is just a general solution. The general one. Any questions? Okay. So I repeat, just now case 1. Case 1 is p equals to 0. This is case 2. Case 2 is p greater than 0. When p greater than 0, we let p to be lambda squared. Okay, but your lambda is positive. Okay, we let lambda be positive. So you just substitute this one into this here, the p. You get the 2 ODE. Solve the 2 ODE separately, then you will get this x in x, t in t, and finally you combine your x and t to get your solution. Your solution is u x t. Okay, the solution is u x t. Okay, now we look at the third case, case 3. Case 3 is p less than 0. So we let p to be negative lambda squared, but your lambda is still positive. Okay, it's the same lambda, but your p is negative lambda squared now. So if your p is negative lambda squared, so we get another 2 ODEs. So x double prime minus, you get a plus p, like no more p, plus lambda squared x equals to 0. And another one is t prime plus, okay, your p is negative lambda squared now, kt. You get these two. Okay, so again, we want to solve this second order homogeneous differential equation. Okay, second order linear homogeneous. So characteristic equation. N squared plus lambda squared equals to 0. So this one, negative lambda squared. So m is plus minus lambda I. This is complex conjugate, so your solution will be alpha is 0, beta is lambda. So here use capital A. So suppose you have T alpha X and then I follow this one, A cos beta X plus B sine beta X. Okay, your alpha is 0, so E0 is 1, so no exponential function. Your lambda, beta is lambda. So you have A cos lambda X plus B sine lambda X. Okay. So you have A cos lambda X plus B sine lambda X. Okay, so far, any questions? Okay, for T is the first order differential equation. So T prime we write as dt over dt. And this one we move it to the right. Okay. So again, T move to the left. dt move to the right, and you integrate both sides. So this one you get a ln T. This is a constant. Then T plus lowercase of c. Okay, then what we want is T in this lowercase of t. The ln here will be exponential. That's mean EC, we assume EC as capital C. Same as the one just now. Okay, so this is your T. Okay, and finally we combine the x to the t. So your uxt is x times t. Okay, this one. A cos lambda x plus B sine lambda x. This C e negative lambda squared kt. Okay, then you can combine the AC and also the BC. Okay, combine the AC and also the BC to be B and E. Okay, so AC is D. BC is E. We just combine the constant because this is not an exponential function. So we don't have to combine. We just leave it like this, but we just combine the constant. AC is D, BC is E. So this is the solution for the case 3. Okay, you can find the answer in the slide, but just that this one is the extra explanation how to get the solution. Okay, this is the extra one. Show you how to get an even solution then. Okay. Now there's a note here. Okay, notice that there are 3 possible solutions. Okay, there are 3 possible solutions. However, with the boundary conditions and initial conditions, this problem has a unique solution. Okay, meaning that if you are given the boundary condition and initial condition, you have only one solution. Here you have 3 solutions. Okay, the general one you have 3 solutions, but for the particular case with the given boundary conditions and initial conditions, then you will get unique solution. Unique solutions means you have only one solution. Okay. Any question? Okay. Now we look at this. So I think if we don't make this one, I just copy the question on the paper. Okay, one exercise. Find the solutions of the heat equation. Find the solutions of the heat equation. This one along a uniform metal rod using separation of variables. Okay, so now we want to solve this. Okay, so first of all, we will change this partial derivatives into their representations. Okay. With the assumption we let u to be x times t. Okay, so this one will be changed into, this is ut. What is ut? X t prime. This one will be 0.9 x double prime t. Okay, now separate. Okay, separate and we leave the 0.9 with the t. Okay, separate. So we have this. Okay. Put the x over here and 0.9 t here. So you get this. And this one equals to p. When this is equals to p, now we look at this one. Okay, this one, when this equals to p. Okay, this is actually x double prime over x equals to p, and also t prime over 0.9 t equals to p. So from here, we will get 2 ODE. 2 ODE. So this one means x goes to the right, and then we move this to the left. Okay, similar to this one. 0.9 t move to the right, it will be multiplication. Then this one move to the left. So we have 2 ODEs. Okay, so we have these 2 ODEs. Now we will start from the case 1. Case 1, your p equals to 0. So you substitute p equals to 0 into these 2 ODEs and start to solve the second order and first order ODEs separately. Find for the x and t, and finally combine x and t to get the final solution u. When P is 0, so you just, so basically, this will be same as the given example just now. So T prime equals to 0, so T will be C. Then your UXT will be X times T. Okay, this is your X. This is your T. Okay, so you get AX plus B, plus B. Okay. AC, we let it be capital A. BC, we let it be capital B. Okay. Then case 2. In case 2, P is greater than 0. That means we let P to be lambda square, where lambda is positive. So we substitute this into your P. Okay. Lambda square into this P and this P. Second order, we use characteristic equation. Real and distinct. same exactly as the one just now. And this T prime we write as dt over the locus of T. Move this to the right. Okay, and move the uppercase T to the left. We separate the variables.
Okay.
So we get the log T is 0.9 lambda squared T plus C. So T is E. That means D capital C. And finally, your UXT. UXT is X times T. So you just combine. About this one. Okay, and for the last case, okay, the last one, case 3, P less than 0. Try to substitute the P with the negative lambda square. Now put this negative lambda square into here. Okay, minus, minus, you get a plus. The one, second order ODE, stop using characteristic equation. Okay, the one, first order, stop using separable first order differential equation. Characteristic equation n squared plus lambda squared. So this one n squared is negative lambda squared. It's mean complex conjugate. Okay. This one how to get complex conjugate. N is square root of negative lambda squared. That's mean. Okay, this one is I. This one is lambda. That's why you get a lambda like plus minus. Yeah, plus minus. X is a plus lambda x is sine lambda x. Alpha is 0, beta is lambda. Alpha is 0, beta is lambda. For the second equation, okay, write the t prime as dt over dt. Move this to the right. Separate. Okay, then separate. Okay, great. Okay, any questions? This is the basic for the next part. Okay, this is the basic. If you understand how to get the x, how to get the t, and how to get a u, Then it will be easier for you later. Yes. Assume lambda. You assume lambda is positive. Okay, we assume lambda is positive. So when lambda square, okay, it will always be positive. Negative lambda square, it will always be less than 0. You won't get this because lambda is positive. You won't get this one. Okay, because this is for case 1. Case 1 is p equals to 0. But for case 2, we want strictly positive. For case 3, we want strictly negative. That's why we have this. When this is positive, when it's square, it confirms won't be 0. When you have negative lambda square, it will be confirms negative value. You won't get 0. Okay, for the second and third case. Okay. Any more questions? No. Okay, next one, we look at the application of PDE. Okay, we start from the heat equation. Today we look at the heat equation. Okay, so in this section, we will study the heat flow problem in a long uniform rod. Okay, this is a long uniform rod. Okay, and these are the boundary conditions. Okay, you see the boundary conditions is always 0. Okay, 0. When this represent the heat equation, that means your U represent the temperature. Okay, U, the solution U represents the temperature. So when your temperature is 0, that means this one, these two temperatures are 0. Okay, we maintain this as 0. Okay, because no matter what is your T, okay, this one, no matter what is your T, your temperature at this point, 0 is always 0. And your temperature at this point, L, regardless what is the T, it is always 0. Okay, you have to read like this. Okay, U is the temperature. And then initial condition. Okay, this initial condition, it means what is the temperature, how you start the temperature, okay, at this rod. And later we will see after a few seconds or after a certain of times, what is the temperature? Okay, what is the temperature of the rod, or what is the temperature of the rod at a specific point? Okay, we want to see how is the heat being conducted. Okay, this one. This problem depends on the initial distribution of temperature. That means the initial condition. Okay, and also the physical properties of rod. This means we look at this one, thermal diffusivity. Thermal diffusivity, heat equation, this one, K. This is the heat equation, and K is the thermal diffusivity. Okay, because if the material will decide whether the heat can be transferred faster or slower. Okay. So by using method of separation of variables, the solution function U represents temperature at the point X along the rod at time T. Okay, at time T. So we can determine, okay, either in general or at a specific point. Okay, we can find for that. Okay. Okay, this is a graphical illustration. Okay, boundary conditions will be given, initial condition will be given. Okay, then we will find for the UXT. Okay, for example, this one, U05, XT, and this is X, this is T. U05 means at time T equals to 5, okay, the temperature is 0, okay, at the rod point 0. Okay, that means at the initial point of the rod, the temperature is 10. And the unit of measurements of length time depends on the unit of this thermal diffusivity. Okay, it depends on this. Okay, so do you understand this one? The temperature of the rod at point 0 at time T equals to 5 is 10. Okay. Now this is the model, okay, for the heat equation. Okay, you have a partial differential equation for heat equation. The length of the rod is L. Okay, the length of the rod is L. You are given two boundary conditions where these boundary conditions, the temperature is always 0 at the starting point 0 and at the ending point L. And also you will be given an initial condition. Okay, this is the initial temperature distribution that you give to the rod. Okay, and so this problem, it has a series solution of this. You will get this solution. And this B is the Fourier series coefficient of this. Okay, but we do not use this directly. We will derive step by step to get this solution. Okay, now we look at the first example. Okay, for the time being, I want you to understand, try to understand every single step on how to get the solutions. Okay, try to understand. Okay, solve this PDE for the heat transfer, okay, by using method of separation of variables. Okay, so the length of the rod is 2 pi. Okay, and this is the heat equation. This is the boundary condition. Boundary condition, it will always be 0. Okay, for this case, okay, for this model, okay, it's 0, and this is your initial condition. Okay, next, by using the first 3 non-zero terms of the series, compute the temperature of the rod at point X equals to pi and for the time T equals to 1. Give your answer to the 4 decimal places. Okay, let's maybe find for the solution first. Once you get your UXT, we use the first 3 non-zero terms to calculate for the temperature of this case. Okay, so this is this one just now. Yeah, this one. So UT is the XT prime. UXX is the X double prime T. So you get this. Okay, this is the first step. Separate the variables. X to the right, T to the left. We let the 9 follow the T. Okay, we let the 9 follow the T. So you have 9T prime over T. Okay, equals to P. Okay, we let the constant follow the first order differential equation. Okay, so because of this, you have these two. Okay, same exactly as what you did just now. And these two, you will get these two. OBE. Okay, now we start from the boundary conditions. Okay, you are given these two boundary conditions equals to 0. Okay, so this one we will write in this form as well. This one we write this into this form. So your U0t, that means x is 0, t is still t. So you have x0tt, this one. Can you see that? This is the given boundary conditions. This is also the given boundary conditions, which we write this into this form. Okay, you have U0t, U0t. So x is 0. So you have x0tt. And another one, x is 2 pi. That's why you have x2 pi tt. Okay, that means this one can be written in this form. Okay, where it is equals to 0 because you are given the initial condition, this u equals to 0. That's why this is also equals to 0. Okay, same goes to this one. Okay, so if you look at this equation, okay, this equation, okay, from the starting from the first place, I have told that our u cannot be 0. Okay, this u is our solution. We do not want our solution to be 0. So it means your x and also or your t, x or t cannot be 0. Because if one of them is 0, your u will be 0. So here we know that your t is not 0. Okay, t is not 0. This one. When t is not 0, that means x0 is the one equals to 0. Okay, same goes to this one. Your t is not 0. Okay, so your x2 pi is the one to be 0. This is not 0, but this one equals to 0. That's why this equals to 0. Okay, remember your t in t is not 0. Okay, so from the two boundary conditions, we get these two. Okay, we get these two. Okay, next we will start to consider the three possible cases for P. Okay, we start with the case 1, P equals to 0. You get to see this? Not sure whether I block your view. Okay, this one from equation 5.6. Okay, that's mean from these two. From these two equations, we substitute P equals to 0. P equals to 0. So we get this. Okay, x double prime equals to 0, and another one is t prime is 0. But we solve for the x first. Okay, we solve one by one. So when we get this x double prime equals to 0, so we just integrate. Okay, we integrate twice, you get ax plus b. Okay, same exactly as what you did just now. Okay, so from here we will substitute the two boundary conditions that you obtained just now. X0 is 0 from here. We will apply these two to find for the a and b values. Okay, so this one, it means when the lowercase of x is 0, the uppercase is also 0. Okay, so this one, x is 0, that means a0 plus b equals to 0. Okay, this is also 0. But a times 0 is already 0, that means b plus 0 equals to 0, which is b also 0. Okay, do you get it? Okay, next we apply this one into this. When lowercase x is 2 pi, your uppercase is 0. Okay, so this x is 2 pi, so a 2 pi plus b equals to 0. Okay, equals to 0. From here, we have already know that our b is 0. So substitute b by 0. You get this equals to 0. It means a is also 0. Correct? So now a is 0, b is also 0. So your x is 0. When your x is 0, your u is 0. So that means this case, it will give a trivial solution. Trivial solutions mean 0 solution. Okay, solution is 0. So we will omit this case. That means we discard this case. We won't use this case. Okay, because it gives trivial solution. Okay, so far any questions? Okay, next we look at the second case when p is greater than 0. Okay, so your p is lambda square. So we substitute the p by lambda square. Okay, just now you have x double prime minus px. So the p is lambda square now. Okay, so here we solve using characteristic equation. Okay, and the roots are real and distinct. So you get this. Okay, this is your x. Okay, now again we substitute the boundary conditions that we obtained just now. Lowercase is 0. Uppercase would also be 0. Okay, so that means this 0, E0 is 1. E0 is 1. That means A plus B equals to 0. Okay, then you get one equation. And on another side, when lowercase of x is 2 pi, your uppercase x is 0. Okay, that means when this lambda is 2 pi, this is also 2 pi, you get this line. But x is 0, so it equals to 0. Okay, so these two, okay, from here, your a plus b equals to 0. We can also have a equals to negative b. Okay, a equals to negative b. So we substitute a by negative b. Then we factorize the b, so you have negative e2 pi lambda plus e negative 2 pi lambda. Okay, factorize the b. Okay, so this is exponential function. Okay, exponential function, it will never be 0. Okay, because your lambda is not equals to 0. Okay, so 1 plus, unless, okay, this can be 0 unless your lambda is 0, then you get negative 1 and positive 1. But lambda is not 0, that means this is confirmed not 0. So if this is not 0, your b must be 0 because this is equals to 0. Okay, so since exponential function, this part is not 0, so that means b is the one to be 0. If your b is 0, that means a is also 0. If a and b are both 0, x is 0. Then your u will also be 0. That means this second case, it also gives a trivial solution. So we omit this case, meaning that our solution will be obtained from the third case. Okay, so far any questions? No? Okay, now we look at the last case. Okay, when p is less than 0, our p is negative lambda square. Okay, so now we substitute negative lambda square into the p just now. Okay, so we have these two. Okay, these two ODE. Okay, we solve for the x first. So we obtain the characteristic equation and we found that it is complex conjugate and hence we get this. Okay, now we apply this one. Okay, we apply these two into this to get the a and b values. Okay, so from the first one, when x is 0, cos 0 is 1. So you have a. Sine 0 is 0, no more b. So a equals to 0. Okay. Then from the second condition, okay, when your x is 2 pi, okay, then you have 2 lambda pi. Okay, x is 2 pi, so 2 pi times lambda, you have 2 lambda pi. Okay, 2 pi lambda, sorry. So you have this a cos 2 pi lambda plus b sine 2 pi lambda equals to 0. Okay, because your uppercase x is 0. So this whole thing equals to 0. But because of a is already 0, we know that this term is gone, meaning that this is equals to 0. Okay, up to this point, okay? Okay, then since this is equals to 0, our b, for sure b is not 0. If b is 0, that means a 0, later on your x will be 0. Then that means we can't get any solutions. So b is not 0. This is 0. Sine 2 pi lambda equals to 0. Okay, when sine function equals to 0, meaning that the angle must be n pi. Remember, sine n pi equals to 0. For a sine function to be 0, your angle must be n pi. So you equal the 2 pi lambda to the n pi. Okay. Then you can find for the lambda. Okay. Cancel out the pi. You have n over 2. Okay. The n is natural numbers. That means 1, 2, 3 up to infinity. Okay. And this one, you see that your lambda is now lambda n. There's a subscript n here because n can be 1, can be 2, can be 3, and so on. That's why we can't say that this is lambda. This is lambda n. That means lambda 1 is 1 over 2. Lambda 2 is 2 over 2. Okay, this is a kind of series. Okay, so now we substitute the lambda n back into this one. We want this. Okay, this is our solution now. X. We are solving for x. So a is already 0. No more. So x is v sine lambda x. Okay, x is v sine lambda x, but our lambda is lambda n. So when lambda is lambda n, means that v is vn, x is xn. So we get this. Then you substitute a lambda n by n over 2. Then you get this for your x, but now we have xn instead of x. Okay, so far, okay? Okay, next we want to solve for t. Okay, we want to solve for t. Okay, this one, okay, this one is same exactly as the one that you did just now. Okay, write t prime as dt over dt. This one moves to the right. We integrate both sides. We get the ln t. Then our t finally will be this one. Okay, when you get this one, your lambda just now is lambda n. So when this is lambda n, c will be cn, t will be tn. So you have tn equals to cn, lambda n. Okay, then you substitute your lambda n by n over 2. This is square, right? Lambda square. So when you square this, you have n squared over 4. N squared over 4 times 1 over 9, you have n squared over 36. Okay? Try to understand at this moment. Try to understand every single steps. Lost? What did you lost? Huh?
She lost from the upper part.
Upper, this one.
The VN sign.
Oh, this one.
Yeah.
Oh, okay. So do you understand this one? This one, okay? B is not 0. If your B is 0, A 0, X will be 0. X 0, that means your U later will be 0. So if B is not 0, it must be sine 2 pi lambda to be 0. Right? It must be this one to be 0 because this product function equals to 0. It must be one of them equals to 0. Okay, since B is not 0, that means sine 2 pi lambda equals to 0. Okay, sine function, for sine function to be 0, the angle must be n pi because we know that sine n pi equals to 0. Right? Sine n pi equals to 0. So for a sine function to be 0, the angle must be n pi. Okay, the angle must be n pi. So that's why 2 pi lambda equals to n pi. So from here we can get the lambda. Okay, so once you get your lambda, because your lambda contains the n is natural numbers. So that's why we no longer address this as lambda. We address this as lambda n. Okay, lambda n. So when this is lambda n, B will be Bn, X will be Xn. No more A because A is 0. Then we get this. And finally, we substitute lambda n by n over 2. Then you get this. Okay? Okay, so this is we have done twice. So you have t equals to this one. Okay, so we substitute the same lambda into this lambda square. Okay, just now you have lambda n. So this will be lambda n squared. C will be Cn, T will be Tn. This one, Tn, Cn, lambda n square. So we substitute this lambda n over 2. This is lambda square, right? So we square this one, you have n square over 4. So n square over 4 times 1 over 9. Then you get n square over 36. Multiplication. Okay, then you have done obtain the Tn. So when you have xn times Tn, the u must be un. Okay, u must be un. So xn just now, this one, Tn here. Okay, when you put them together, okay, we can combine the Bn and Cn as Dn. Constant. We combine the constant as Dn. So we have sine and exponential function. Okay, this is your un. Okay. Okay. Remember, our solution is u, not un. Okay, our solution is u. We don't want un, so we want to change the un back to u. Okay, so we have to apply the superposition principle. Okay, that means your u is this one. From un back to u, we will sum up. Okay, we will sum up this one. We sum up all of the terms from 1 up to infinity. Okay, we sum up all of the terms from 1 up to infinity. This one, from 1 up to infinity, all of the terms on the right just now, when we sum them up, your un will be u. This one, okay?
Okay.
Then we will start to apply the initial condition.
Okay.
Okay, initial conditions. When t, this is given. Okay, this is given. When t is 0, this one, when t is 0, what's happened to this one? E0. E0 is 1. So you have only dn and sine function. Okay, and this one will be this one, right?
Yes.
Then you get this. So what we want to find now? Dn. We want to get the dn. Okay, recall from the Fourier sine series. Okay, Fourier sine series, you have learned this one. When this function equals to the summation of bn sine and pi x over L, this is Fourier sine series. Your bn, we use this formula. Now, this is similar case. This is your fx. This is your bn. And your L, what is your L?
2.
N pi x over L. Pi? Pi over 2. 2 pi, right? 2 pi. Your L is 2 pi. We cancel out the pi, so we get over 2. And remember, your L is the length of the rod. The length of the rod just now given 2 pi. Okay, so we will use this formula to find for the dn. Okay, so dn is, we use the Fourier sine series formula, where your fx is this function, L is 2 pi. Okay, then substitute L by 2 pi. 2 pi. Okay, when you get this, simplify, cancel out the 2, and this is polynomial with sign. So we use tabular method. Okay, we differentiate respect to x until you get 0. This one, integrate 4 times. Then you get this line. Then substitute 2 pi and 0. Simplify, you get this one. This is your dn. Okay, this is what you have learned from the previous chapter, Fourier series. We are integrating the basic from the Fourier series and also the chapter 1, chapter 2 into this last chapter. Okay, so now you have get the dn. What is your dn just now? This one, here, right?
Yeah.
Remember, because sometimes when you find after you finish one step, you will tend to forget what you want to do next. So when you have already forgot, okay, for example, you have already get the n. So what is the next step? Okay, if you forget what is the next step, refer back to your final solution. Remember, your final solution is always uxt. This is what you want to get. So once you get your dn, you just substitute your dn right into here to get your final solution. Here, dn, once you substitute your dn, you get your final solution. This is your uxt. Okay, and from the questions just now, it mentions that use the first three non-zero terms to compute the temperature of the rod at point, time, and t equals to 1. They use the first three non-zero terms, meaning that we will expand this one. Okay, we will expand this one. Okay, I think you will stop here, right? Because this is your dn. So that means you will start from n equals to 1. You substitute 1, 1, 1, 1 here. Okay, then you will get this. When n is 2, here this one, when n is 2, negative 1 square is positive 1. 1 minus 1 is 0. You get 0 for n equals to 2. Then n equals to 3, you get a non-zero term here. N is 4, 0. N is 5, you get non-zero term. So these are the first three non-zero terms. Then you just compute using a calculator, you will get this. So this is the temperature, the specific temperature. Any questions? Because in the question, it wants you to use the first three non-zero terms. First three non-zero terms. So after you expand, you substitute, and you found that when n is 2 is 0, that means you have to find for the next one. N is 3. And then n is 4, again 0, then use n is 5. As long as we want the first three non-zero terms from this series. From here, from the last one. Okay, this one, you can also present your answer in this form, okay, because we know that whenever n is even number, you get 0. So it will be n odd. Okay, it will be n odd. For n odd, you get 1 minus negative 1, which is 2. 2 times 16, you get 32. Okay, but you can stop your answer here.
Oh, but this one, case one, let's say we already get a value from case one, so we need to continue for case two.
You will always get 0 for case 1 and case 2. You will always get 0 for this case, for this model, because we fix the two ends point as 0 temperature. Okay. So for this model, because there is more than one model for this heat equation. Okay. So for this specific model where the both temperature, both endpoints temperature is 0, okay, your first two case will always be 0.
We jump into the case two.
It depends on the question. If the question mentions that use list out all three possible cases, then you list out all three. If it mentions that use only the case 3, then you just jump into the case 3. Okay, any more questions? Any more questions for this one? This one, assignment. Assignment. Analytical. Solve the PDE using analytical method. That means the method of separation of variable is covered under your assignment. Okay. Assignment is the points that confirms you can obtain right before your final exam. Right? Discuss among your members. Okay. So
Question one.
if possible, you can get score. Try to score. Okay. Now we look at the second example. Okay, second example, your L is pi. Okay, your L is pi now. And this is your PDE. Okay, both boundary conditions are 0. So the steps are almost the same. Okay, write out the representation, separate the variables, break it into two, obtain the two ODEs. From the given boundary conditions, get these two. Similar, okay, then we will start to consider for the three cases. Start from the zero, case one, p equals to 0. Then you get this one, integrate twice, you get this, substitute this one, you get b0, substitute another one, a0. When a and b are 0, x is 0, that means u is 0. We omit this case. Okay, second case, p greater than 0, that means p is lambda squared. Okay, where lambda greater than 0. So we substitute p equals to lambda squared into the equation just now. Okay, so we get this one. This one, get the characteristic equation, and we found that the roots are real and distinct. So you get this. This one, apply these two. Okay, first one, from the first one, you get one equation. From the second one, you get this one. So substitute a by negative b, factorize b, and we found that this cannot be 0. Exponential function, it will never be 0. So the one to be 0 must be b. So when b is 0, a is also 0. That means your x is 0. X is 0, that means u is 0. We omit this case. Then the last case, p is negative lambda squared. So we substitute this one into the two equations just now, then we get these two. Okay, we solve for the x first, characteristic equation, and we found that it is complex conjugate. That's why we get this. Apply the first boundary conditions, we get a equals to 0. Apply the second boundary conditions, we get this line. B cannot be 0, so sine function is the one to be 0. So for sine function to be 0, your angle must be n pi. And hence you get your lambda, which is lambda n equals to n. Then when your lambda is lambda n, that means lambda n, bn, a is already 0. So x will be xn. Okay, so finally substitute your lambda n by n. Then you get xn. Then we look at the second equation. Okay, solve as usual this one until you get this one. So this is lambda n, this is cn, this is tn. Okay, lambda n squared. So we square this, you get n squared. So you have negative 4n squared. Once you get your tn, combine tn to the xn, you will get un. Okay, then this bn cn, we can let it to be a new constant dn. Okay, then this is your un. Okay, next we want to get u. Remember, from un to u, we just sum up this from n equals to 1 up to infinity. Then your un will be u. Okay, sum up the right hand side function from 1 up to infinity. Then we will apply the initial condition when p is 0. Okay, when p is 0, e0 is 1. So we have only this. And your uxt will be 2 sine 3x. Okay, this one, when your initial conditions is a sine function, it will be, you have two choices, whether you want to use this to integrate, or there's another alternate way, which is very simple. Okay, this is for if you use the Fourier sine series integration method, you will get this. But because of n is not 3, okay, n is not 3, you have to solve specifically for n equals to 3, for the case of n equals to 3. Okay, this one is a bit long. Okay, there is another way, a simple alternative way to get the dn. Okay, this is what we had just now. So this is summation, meaning that we can expand this one. We can expand this when n is 1, you have d1 sine 1x. Plus, when n is 2, you have d2 sine 2x. And so on. Okay, on the left, we have this. So you just find this is 3x. 3x. That means your d3 is 2. And the rest of the d are zeros. You get what I mean? Expand this one. Expand this one, because this is also sine function. We can compare on the left and on the right. This is sine 3x, so we compare with sine 3x. So d3 is 2. And d1, d2, d4, and so on are zeros. Okay, so the only possible Dn is D3. Okay, D3 when n is 3. The rest are 0. So when n is 3, okay, go back to your solution. We want n is 3. Okay, this is your solution. We want only n is equals to 3 because the other values of n are 0. So D3. So when n is 3, we have D3 sine 3x e negative. This is 9. 9 times 4. So 36t, negative 36t. So you write this out, you get this. When n is 3, when n is 3, you get this. So this is your solution. You just substitute D3 by 2. Then you get the final solution. Okay, that means when for heat equation, when your initial condition is a sine function, you can use this way. This is much simpler without the need of finding for Fourier sine series. Okay. Okay. I think today we stop here. We will try the exercise in the next class, next week. Next week. Sorry. First day.
Ada, untuk ada yang baik. Nampak. Boleh.